Welcome learners. In today's lecture, we are going to look into different scenarios where the Gauss's law is not symmetric, or we can say that the Gaussian geometry is for asymmetric surfaces, and what happens to the charge distribution in that scenario. So till now, we have applied Gauss's law to a symmetric object, whether it was a point charge, line charge, or a coaxial cable. So the symmetry of the imaginary Gaussian surface was spherical or cylindrical. But what happens if we have the Gaussian surface as shown over here to be asymmetric? Then how we are going to solve this kind of a problem? Obviously, when we have an asymmetric Gaussian surface, the constant d assumption, or having a similar or same value everywhere on the surface, is not possible. So our analysis now has to be changed. So in order to do the asymmetric analysis, we will start by choosing a very small closed surface. We will say that we have a very small closed surface that will be represented by, let's say, this operator of a differential operator d, and the value of d will now be constant in that small area. For example, if this is my asymmetric surface, I can select a very small portion calling it as delta d, and now the value of ds will be constant over this small selection, and then we can analyze what happens to the value of d over this surface when we move d in small steps. So in order to solve the variation of d, we will make use of what is known as the Taylor series expansion. So Taylor series is going to help us solve the variation of electric flux density in this small vicinity. So it means what happens when d moves in one direction, the other direction, or in the opposite direction. And then later on we are going to consider the small volume inside differential element equal to 0, that we are going to look shortly. So before we continue, what is a Taylor expansion? So Taylor expansion, you might have seen in your calculus course, is represented as such. So if we have a function f of x, the Taylor series is basically used to provide a solution to complex functions using simple polynomial expressions and derivatives. So the Taylor series is written as that can be f of n to the a divided by n factorial and then x minus a to the power n. So in our analysis, we are just going to use the first two derivatives and find the variation in d, that is the electric flux density. So the Taylor series is used to solve the variation for d, and in doing so, when we are dealing with the variation in d, we will reach to something which is known as the first Maxwell equation. So we will come to this equation as well. So as you can see in the image on your left, we have a heart-shaped structure where the charge plus q is placed, and it is now having a Gaussian symmetry represented by this dotted red cover, which is asymmetric in nature. So how can we solve these kinds of problem? So in order to solve these kinds of problem, we are going to consider a very small portion inside this asymmetric geometry and call it d, or partial d, and then we are going to see what happens when this d is moved slightly. So let us observe this portion, or focus on this small portion, and see how can we find the equation for the Gauss's law for the asymmetric surfaces. So now let us take the small portion as over here and zoom it, and such that it becomes a very small differential volume element, and inside we have enclosed a point called P. So this is in the Cartesian coordinate system. You can see with the axes y, x and z, and the differential elements for this rectangular box is delta x, delta y and delta z, and the point of interest is P, located at a certain point of x naught, y naught and z naught. So what is the electric flux density for this small differential volume element? Obviously this is the d which we want to know, and the d is moving in various direction, but it is not uniform because it's an asymmetric object, and we have chosen a very small differential element on that asymmetric geometry. So according to the scalar and vector notation, we can represent D as such. So D will have a value of the scalar component along x in the direction of A of x, and it will have the scalar component along y in the direction of A of y, then along z in the direction of unit vector A of z. So this is the generic equation to locate electric flux density for the point P, which is inside this differential volume element. Now if you look at this differential volume element or cube, it has 6 faces. So we want to find the value of ds, so we can apply the Gauss's law. So Gauss's law is basically the charge enclosed can be found by the closed surface integral of the electric flux density and the small area which I have selected. Since this cube has 6 faces, so we need to solve the integral, this one, for all or every face. So the face will be for the front, back, left, right, top and bottom. So let us solve for one of the faces. So let us say I want to solve the integral for the front face, which means my integral will be d, let's call it of front, and the small area for the front value d of s. Now what is the value of d of front? So assume the point, so let me say the point, I'll clear this. The point is at the back of the axis over here. This is on the back face, and now d is basically the electric flux density which is coming from the behind and moving towards the front end. So this is the value of d. So I can write what is d front. The electric flux density moving towards the front is basically the point d of x with the unit vector a of x, because the electric flux line is coming from the back and moving towards the positive axis, and this is the x-axis. And what about the d of s, the small area for the front scenario? So obviously if we look at the area in the front, we have this face which is only having the value of delta y and delta z, and since this is a sheet in the front, so the normal vector will be along a of x. So if we incorporate these two values into the integral, we get d of x along unit vector a of x dot product with delta y, delta x, delta y and delta z with the unit vector a of x. Our solution then comes out to be dot product of unit vector with unit vector results into 1, so we'll be left with d of x, delta y and delta z. So this is the equation for the integral that is the front face of the cube. Now let us try to solve the value for d of x front, because we know that the integral has these values, but we still don't know how to find d of x. So now let us write the equation again. So for the front integral, we simplified it to d of x front along with the front parameters of the sheet, that is delta y and delta z. So now let's solve for d of x front, and as I mentioned, d of x front is basically going to be solved by the Taylor's expansion, or especially the first two derivatives of the Taylor expansion series. So how can we solve it? So d of x front, what does it mean? So it means that if we go back to our axis and the cube, it is how much we are moving from point P towards D. So what is D along the x-axis? So what is the electric flux density that is moving away from point P? So this is going to be d of x, plus we want to take the first derivative and the second, so it means that the motion that I have covered from point P to x is the distance, that is delta x divided by 2, and how much d has varied from point P to x is basically represented by the partial derivative of d along x. So this is what we are getting for the value of d of x front, that is extracted from the Taylor series. So visually we can see that dx is the point of interest along the x-axis. So we want to see how much is the D, that is the electric flux line coming from point B towards positive X, then how much D has basically moved, so it has moved a small step from the origin towards delta X, and how much is the change in D, so that is the partial derivative coming into the picture. So once I have this, I can go back to my integral. Let us say this is my equation 1, so I can input the value over here. So my integral now comes out to be d of x plus delta x divided by 2 partial derivative of d of x, and this is getting multiplied with the small surface face in the front of dy by dx. Similarly, let me call this equation 2. Now let us find the integral for the back of the cube. So again, for the back of the cube, we have to write this equation, that is now in d back by ds back. So integral will be ds back with partial derivative this surface area of back, the integral. So now what is dx back? Again, go to the image. Now I want to know what is happening from point P when the dx is along negative a of x. So my equation for dx back would be, so I'll write it over here, dx back is going to be dx, but it will not be negative ax but positive a of x. Why? Although I am interested now in the point that is on the back side, but electric flux is entering from point B and moving away from here. That's why we haven't taken negative a of x, we have taken positive a of x. And again, the ds back is going to be the phase that will be on the back of the cube, that will be delta y delta z, but this time the unit vector will be negative a of x. So now I have this value, so I can write it over here as minus dx back, and this will be delta y delta z, and since this is ax and ax, so it will become 1. So now let us see what can be the value of this back equation. So obviously it is going to be the same scenario as was with equation 2. It will going to be negative dx plus delta x by 2 partial derivative of d of x along with x, and it comes out to be delta y and delta z. So this is one way to find the value of the back end or back surface of the cube, and you can also look into equation number 2 and just change the sign to get the equation 3. So now once I have these two equations, what I can do is I can add the front and back integrals to get a single value. So you add equation 2 and 3, so you will get partial derivative of x along dx, and the common value is for x, y and z. So this is equation number 4. So now once we have the front and back, we can complete the summation of integrals for the left, right, top and bottom. The only differentiation will be that my left and right, so if I write the equation for my left and right, and then I write the equation for my top plus bottom, that would be, so the left and right is having the values of y-axis, so I can just replace dx with d of y, but this will be partial derivative along y, and the main steps will be the same, that is the small differential elements will be x, y and z, and for top and bottom this will be along z, and the elements will be dx, dy and dz. Now I need to add all the equations, that is equation 4, 5 and 6, to get a single equation out of this. So adding all these equations, equation 4, 5 and 6, I can get the final equation for asymmetric Gaussian surfaces as such. So the charge for the asymmetric Gaussian surface is equal to the total charge enclosed on that surface, that is d dot ds, and that equates to the differential volume element, or we can say the partial derivative of dx along x plus partial derivative of dy along y plus partial derivative of dz along z. And if you look at all these three values, delta x, delta y, and delta z, in equation 4 and 5, 6, that corresponds to the volume or differential volume element delta V. So this is the equation or the Gauss's expression for asymmetric charges, where we rely on the partial derivation, and it literally means that if we have any point, let's say if I have any charge over here and we want to know how much the charge energy is in an asymmetric geometry, let's say this is an asymmetric Gaussian surface. So what we'll do is we'll select a small portion, we'll apply the analysis, and we will say that in this small portion the d is going to have a constant value, thus its variation will be based on the value that we have calculated for the asymmetric surface, which is the Gaussian equation, and that is relying on the movement of d in small vicinities. So this is the equation for the asymmetric surface, and you can say it is also relying on this small volume charge that is enclosed inside this smaller patch. So again, this portion here represents the variation of electric flux density, in the axis, and this is the small volume enclosed. Again, the focus is on this portion of an asymmetric geometry around any closed charge. So remember this equation for the asymmetric charges. So now let us look at an example of how we can find the Gaussian charges, or how can we apply the Gaussian equation on an asymmetric surface. So let us say we have to find the electric flux in this differential volume element, and we have been asked to approximate the charge in a volume of 10 to the power minus 9 meter cube, where the electric flux density is such. So we need to find what is the approximate value of the charge. So this means the question is asking us what is the approximate value of the charge when we have an object that is enclosed in this small differential volume, which we call as delta V, having a value of 10 to the power minus 9 meter cube, and we have been provided the specific electric flux density, which is e raised to the power minus x sine y along ax minus e raised to the power minus e power x cos of y along ay, and plus 2z along a of z coulomb per meter square. So let us solve this. So we know that if we have a differential volume element in an object is enclosed in that small differential volume, the charge is basically represented as, or we can find the charge enclosed by taking the partial derivative of that element along x, partial derivative along y, and partial derivative along z multiplied by the total volume enclosed. So this is the equation that we want to use. So let us find the partial derivatives one by one. Let us find the partial derivative with regards to x. So we know that is going to be the partial derivative of x e raised to power. So in this equation of d, we are only going to focus or find the partial derivative with the components that has a value of x. So it is going to be e raised to power minus x sine of y minus e raised to power minus x sine of y. Again, we take the partial derivative only associated with that value, which is x. Now let us just find the partial derivative along y in the same equation. So we have partial derivative of y. We are going to take minus e raised to power minus x cos of y. It comes out to be e raised to power minus x sine of y. So this is the third one. What about the partial derivative along z? So in the whole expression, the only component available along z is 2 of z, so it comes out to be 2. So now once we have this, input all the values of partial derivatives into the equation and to get the total charge that is required. So the value of q comes out to be partial derivative is minus e raised to power minus x sine of y. Then you have plus e raised to power minus x sine of y and plus 2. So this and this cancels out, so we are only left with 2, and that's it. So 2 is the answer that we are getting for this, but we missed one thing, that is what's the value of delta V. So we multiply it with by delta V, where delta V is 10 raised to power minus 3 coulombs. So this is the charge that we are getting for this problem. Again, applying the partial derivative to the matter. Let us look at another example and see what can we do further with partial derivative. So in this problem, we have been given the electric flux density D, and we are asked to find the total electric flux, which means we need to find sigma or psi passing through the rectangular surface for z is equal to 0. Y and x values are given in the az direction. Then in the second part we need to find the electric field intensity at this point, and in the third part we need to find the total charge contained in the incremental sphere located at point P having a volume of thus. So here we need to find Q in the third part. So let us start solving with the first part. So in the first part we have been given the information that we need to find the electric flux with the symbol of psi. The ranges for the Cartesian coordinate system for x is from 0 to 2, y is from 1 to 3, and z is having a definite value of 2. So we know that electric flux is equal to the total charge enclosed, and the charge enclosed can be defined as a surface integral of d dot d of s. Since this is a rectangular coordinate system, so we know that the surface charge for the rectangular coordinate system depends upon the incremental elements, which is dx, dy and dz. Since our analysis is along z as it has been given as in the az direction, so we are going to ignore, sorry about that, we are going to ignore the z component, and our value will be d of x, d of y, and the unit vector for the surface will be along a of z. So this is the value of d of z. What about d? So d is provided in the question, so let us integrate this. So this comes out to be, we are going to put in the values first, and since this is a surface integral, so we are going to use a double integral. The direction is along az, so our integral will be on x and y. The value of d is 8x y z to the power 4 along a of x plus 4x square z4 a of y plus 16x square y z cube a of z, and then you multiply it or have the value of d of s, which is along dx, dy and a of z. Okay, so before we proceed with the integration or the double integration, we need to eliminate a few things. Eliminate what? That this section is getting multiplied with the differential element, and that has a unit vector of a of z. So we know that the dot product of az with ax is equal to 0, ay az is equal to 0. So automatically this term cancels out, this term cancels out. We are only left with the third term because dot product of az with az is equal to 1. This means our integral will be now a simple one. So that will be x and y. Value is 16 x square y z cube along a of z. So since az has been equal to 1, this is now the integral that we want to solve, that is with dx and dy. So the value of x is from 0 to 2 and the value of y is from 1 to 3. So once we solve this integral, it should be that the coefficient goes out, in the sense I can take 16 and z cube will be outside. And what else we have? So if I am missing something, okay, I forgot this. This is picocoulomb. So I need to add the picocoulomb value of this as well. So let's put it as 10 raised to power minus 12. Then z cube goes outside, and then I can apply the integral as such. So now my integral will be with y and x. So let's go with x from 0 to 2. This is x square, and then I can have integral for y from 1 to 3, that is y. So you can have dx and dy. So then it comes out to be 16 into 10 raised to power minus 12 z cube, and inside this becomes x cube by 3, and the limits are 0 to 2, and the other one comes out to be y square by 2, 1 to 3. So once you input everything, your answer should come out to be 1365 picocoulomb, and that is the charge, and which indeed is the electric flux that is required. So this is the solution to the first part, that is part A. So now let's come to the solution of the second part, which is part B, and let me change the color over here. So in the second part, we need to find the electric field intensity at point 2, minus 1 and 3. This is a straightforward problem. So because we already have D, so we can use the relationship. So we need to find the electric field intensity at point 2, minus 1, 3. 2, minus 1, 3. So we already know that the electric flux density is equal to epsilon into E. So we can use this equation. We have the value of D. So D is basically, I'll write the value of D over here. So electric flux density is 8xyz for A of x. So 8xyz of 4 A of x. Then you have plus 4x square z of 4 A of y, and then you have plus 16 x square y z cube A of z. So what is the value of p, 2 and 3? So you just incorporate x is equal to 2, y is equal to 1 and z is equal to 3 in this equation. So it will going to be 2 minus 1 3 to the power 4 plus 4 1 square 3 to the power 4 for A of y plus 16 2 square, then you have 1 and you have 3 to the power of cube. This is minus 1. So once you incorporate this, you should get the value of minus 1296 along A of x, then plus 1296 along A of y, minus 1728 along A of z, and all this is having a value of picocoulomb, which is 10 raised to power minus 12. So once we have the value of D, just incorporate everything over in this equation. So electric field intensity at point P comes out to be, so I'm just going to, so the value will be D, and the value of epsilon in vacuum is 8.85 into 10 raised to power minus 12. So the answer comes out to be minus 146.4 along A of x plus 146.4 along A of y minus 195.2 A of z volts per meter. So this is the electric field intensity which we are getting. We need to confirm it. Yeah, we are getting this. So this is fine. Now let's come to the final part of the problem, and that is part C. In the third part, we have been asked to find what? So in the third part, we need to find the total charge contained in the incremental sphere P, which is 2, minus 1 and 3, having a volume of 10 raised to power minus 12. So again, we have been given the volume, which is 10 raised to power minus 12 meter cube. The point that we want to find is 2, minus 1, 3, and we need to find the value of charge q. So again, we can apply the equation for the asymmetric Gaussian surface, which is equal to partial derivative of x along x, partial derivative of y along y, plus partial derivative of z along z multiplied by the given volume. So we have the value of d. So the d is this one. So let's apply directly to the partial derivative over here. So partial derivative um, of d of x along x, partial derivative d of y along y, and partial derivative z along z. So in this equation, for the x we get 8yz4. So this is the first term, 8yz4. Then for y we look at the equation, there is no element of y, so this becomes 0. And in the third part, for z we get 16x square y and z power square, so 2 get multiplied with 16, so I'll get 48 x square y z power square. So this is the variables for the partial derivatives which are given applying in this equation. So value of q comes out to be 8y z power 4 plus 48 x square y z square, and don't forget the value of pico, 10 raised to power minus 12 into 10 raised to power minus 12 for the value of delta v. Now we just input the value of p as 2, minus 1 and 3 over here, so the final answer comes out to be minus 2376 into 10 raised to power minus 24 coulomb. This is the charge on the asymmetric Gaussian surface, and let us verify this. Yeah, this is almost the same. So this is how we solve the problem associated with asymmetric Gaussian surfaces using the very important equation of the partial derivative, which is this one. Now let us come to another topic that is associated with asymmetric Gaussian analysis, and that is the topic of divergence. So what is meant by divergence? So keep in mind, divergence is a mathematical tool that basically gives us the flow of the vector, or where the direction is mathematically of the vector. So we can say divergence basically tells us how much spreading is happening naturally, spreading nature of the field. So this is the mathematical way to analyze. We already know about electric flux density, that basically gives us the physical interpretation of the field, but divergence gives us the mathematical explanation, or it's basically telling us mathematically that where the fields is spreading out. So this is what divergence is. So previously we have seen that if we have an asymmetric Gaussian surface, we can find the total charge that is equal to the charge enclosed in that surface by the partial derivative equation. So this is an important element over here. Now what we normally did was that we selected a small differential element, and then we selected a point, and from there we figured out how much the partial derivative will be from this originating point if there is a charge over here. So we can mathematically now assign value to it, and that is called divergence. So what happens is, let us take the previous equation and now consider that delta v approaches to 0. So you want to bring delta v equal to 0. So in the above equation we divide this by delta v. So then we get delta v over here, and this also becomes delta v. So hence we have this second equation where the electric flux density in a smaller region is divided by per unit volume that is tending towards 0. This equation cancels, so we are left with this portion of partial derivation. Again, keep in mind that this portion tells you the variation or a small variation of the electric flux density along x, y and z. So now if we make or tend delta v tends to 0, we can apply the limiting sign to the above equation, and thus this expression over here is the mathematical representation of what we call as divergence of d. So it means that we can state this equation as such, that divergence of a vector flux density is the output of the flux, or let's first keep this equation in mind. This represents the divergence of electric flux density d, where you can see it depends upon the electric flux density d in a small area per unit volume which is tending to 0, and which is equal to the variation of d in small x's as x, y and z represented by the partial derivative. Keep in mind, this is divergence can be applied to any vector. Here it is applied on d, which is the electric flux density, but we can apply it to any vector field. Let's say we apply it to a vector called a. Then divergence of A is defined as symbol divergence of A, which is basically limiting delta V tending to 0 1 by delta V, and this is the electric field in that small electric flux, or the vector flux to be precise, any vector flux in this small area delta S. So mathematically this is how we write it, and its definition is as such: the divergence of a vector flux density, which is A, is basically the outflow of the flux from this region, which is delta S, which is a closed surface, per unit volume, which is shrinking to 0. So this is how we define the divergence of any vector. Similarly, if we want to define divergence in different coordinate systems, so we can define it in the Cartesian, cylindrical and spherical coordinate system, and these are the representations as per their axes. In the Cartesian system it is along x, y and z. In the cylindrical systems it is along rho, phi and z. In spherical it is along r, theta and phi. So you have to remember these representations of finding the divergence of A. So in simple words, divergence can be represented as such. We can say that, for example, if we have any point or where we have a charge, let's say it's a source, so divergence for this case will be a positive value because it is originating the energy. If we have a negative charge, divergence in this case mathematically will be a negative value because it is acting as a sink. But if we have a point where the divergence is entering and then leaving, so we say divergence in this case is 0, or to be more precise, divergence of that vector is equal to 0. So keep this in mind, that how the divergence work. And again, divergence tells us how much flux is leaving a small volume on a per unit volume basis, and it is not associated with the direction. So for direction we have the electric flux density. So divergence is basically a scalar quantity for that matter. So now let us see how can we use these equations to reach to the first equation, which is known as the Maxwell's point form equation. So if we combine the two equations of divergence, what does it mean? That if we have the equation of divergence as such, divergence of D is the partial derivative of x, then the partial derivative of y along y, and partial derivative of z along z. This is the first equation which we found for the asymmetric Gaussian surface. And then divergence of D is also equal to the limiting representation of volume tending to 0, and then you have the surface charge d dot ds divided by delta V. So these are the two representations of the equation. If we combine equation 1 and 2, we reach to what is known as the Maxwell's first equation, which means that divergence of D is equal to rho V. So this is the Maxwell's first equation, also known as the Gauss's point form equation, or it's also known as the Gauss's differential equation of Gauss's law. Why it is called, or it is associated with Gauss's? Because you can see we have a rho V, and if you remember, rho V is equal to the charge per unit volume, so that's why it's a point charge or a Gaussian point form equation. So this is the important Maxwell's first equation, which is telling us that divergence of any vector, in this case divergence of D, is equal to the volume charge density, which is equal to rho V. So volume charge density is equal to Q, and if I further represent it, Q can be written as d dot d of S divided by V. So if it is delta V, a small value, then this is also equal to volume charge density. So this is the Maxwell equation, which basically tells us, so this equation is telling us that the electric flux density, which is D over here, which is per unit volume, is leaving, per unit volume, that is leaving a vanishingly small surface, small volume unit, is equal to the volume charge density. So this is what the equation is saying. This is the definition of the Maxwell's first law. And we can visually see that as well, that what is the meaning of this divergence of D is equal to rho V. For example, for this Maxwell's equation, you have to keep this equation in mind. Let us understand. So definition is the electric flux density per unit volume, which is this portion, leaving a very small volume unit, is equal to the volume charge density. So how can we visualize it? So we can visualize it as such. So for example, consider that we want to find the divergence of D in a region about a point charge which is located at the origin. So for example, if I have this point charge Q, it is located at the origin and it is surrounded by a Gaussian surface, and we know that it is going to radiate, or it is going to pass through a small surface, and then we can find the electric flux density along, let's say, AR. Okay, and this is again my Gaussian surface. So this is the charge at the origin and the distance over here is R. Okay, so now if this is the scenario, what is the divergence of D for this scenario, a charge placed at the origin? So we know that the electric flux density of a point charge is given by this expression, which is the charge per unit the area. Now divergence of D for the spherical coordinate system, says Gaussian surface is a spherical nature, is represented by this equation, which you have to remember. Now since the direction is along the radial component, so the theta and phi element are 0, so we are left with this equation. Now in this equation you can see that divergence is 0 when the value of R is not equal to 0. What it means is, why it is coming to 0, because when you incorporate the value of D in this equation, you are given the value of Q divided by 4 pi R square, where R square and R square cancels out. So once you take the partial derivative of a constant, it comes out to be 0. So what this equation is telling us, that whenever you have a value of R that is not 0, so where is R 0? At the origin. So whenever the value of R is not 0, or whenever you have any point that is other than the origin, the divergence will be 0, which means that divergence is only going to exist whenever we have a charge. So whenever there is a charge, divergence is going to exist, because in the beginning we said divergence means spreading nature of the vector fields. Similarly, if we complete this equation and say that if divergence is equal to 0 when value of R is not equal to 0, but for the value of R when it is equal to 0, which means that we are at the origin, then what is going to be the value of volume charge density? It is going to be existing everywhere, which is 0. So it means that if the charge is at the origin where the value of R is equal to 0, volume charge density is going to exist, but it is going to be 0 everywhere else. So it is going to be 0 for this condition, but it is going to exist at R is equal to 0. So this is a visual illustration of the Gauss's point form, or the Maxwell's first equation. So this concludes our today's lecture.